Hello, and welcome to a very special episode of NASA Science Live. I'm your host, Tahira Allen, and today I am so thrilled to be talking to you about another key milestone in the James Webb Space Telescope's journey to unfold the universe. The past month has been so exciting for Webb, from the breathtaking launch in French Guiana on Christmas Day to the 2-week unfolding of this intricately packed telescope. And now the excitement continues. Not only did everything deploy properly, just as expected, but moments ago, the James Webb Space Telescope completed its final burn and has now arrived at its final destination. Today, we are going to be talking about what's next for Webb as it embarks on its mission to uncover more about our universe and our place in it. We have a lot of viewers who are very interested and just excited about this mission. And today, we want to hear from you. For those watching live, feel free to participate in today's show by submitting a question on social media using the hashtag #UnfoldTheUniverse. You can also drop a question directly into the comment box wherever you're watching the stream from. We will be getting to those questions live on air, so stay tuned. Joining me today are two very special people who are here to answer all of your burning questions. We have Dr. Amber Straughn, who is the Webb Deputy Project Scientist for Communications at NASA Goddard, and Scarlin Hernandez, who is the Webb Flight Systems Engineer at the Space Telescope Science Institute. Ladies, thank you so much for being here today. We are so happy to have you.
Thank you for inviting me. I'm very happy to be here.
Yeah, thank you. Very exciting day. Good to be here.
Yeah, I mean, absolutely. So I can only imagine that you two are on the edge of your seat with Webb having finally arrived at its new home in space. Scarlin, can you walk us through a little bit about what had to happen today to ensure that Webb arrived safe and sound in its new orbit?
Absolutely. So as I was saying, I'm super excited. We're fully deployed, and just about an hour ago, we performed our final mid-course correction, which was about 5 minutes in duration. And here, actually, you can see a live feed of the Mission Control Center. This is actually the launch and commissioning support room where all of the spacecraft engineers and subject matter experts are located. And I can see here on the bottom right, there's Perry. He's the lead of from our thermal team. I see flight software right behind there. And I see some from our power team, our communications team. So it's all hands on deck here. Of course, we have the Delta V team, or change in velocity team, that helped us get into our L2 orbit today. So as I was saying, super excited. We, of course, had a series of steps to take to ensure safety, like making sure that our stored system momentum was below the expected threshold. We had to uplink our ephemeris, which is basically a table of our expected positions on each axis over a period of time. And we worked very closely with the flight dynamics team for the positioning data and these burns. We also had to activate specific heater groups to ensure that we were warm enough to start. And then we were able to beautifully execute the burn, which, like I said, was about 5 minutes. And so we're now at our orbital destination and soon enough be able to make amazing discoveries.
Wow. Thank you for walking us through that. It sounds like a lot had to happen today, and that's basically how this past month has gone for Webb. So much had to go right to get us to even this moment that we're here at right now. And so, Amber, could you briefly describe the past 30 days for Webb and help us understand what all had to go perfectly to get Webb to where it is right now?
Yeah, wow, what a ride this last month has been. I mean, it started with this spectacular launch on Christmas morning. What a beautiful thing to happen. And you know, the launch itself was super efficient, just almost perfect as it could go. And so, thanks to our ESA partners and Arianespace for providing us with such an awesome rocket. And then, of course, the hard part started. The next 2 weeks were filled with these intense deployments. And this is the first time this has ever been done like this in space, the first time anything like this has been done in space. And those deployments also went almost perfectly. We couldn't have asked for a better deployment sequence. And these engineers have built us an awesome telescope. And then the last 2 weeks have really been filled with the telescope continuing to cool. And of course, it's been traveling out to this L2 point and really getting the mirrors ready for this next big phase of commissioning, this 3-month mirror alignment process.
Wow. Thank you for painting that picture for us. It sounds like it has been an intense past 30 days. And it's incredible to hear how all of these teams from around the world, honestly, have had to work together to ensure that this revolutionary telescope is safe and sound and operating where it should be. So like you just shared, we have seen a successful deployment of Webb now. And just today, it has arrived at its final destination in space. But before we go any further, let's learn a little bit more about Webb's new stable home in space at Lagrange Point 2.
The James Webb Space Telescope will perform its science mission while orbiting a location in space 1 million miles away from Earth, called the second Lagrange point, or L2 for short. L2 is a point where the gravitational influences of the Earth and Sun and motion of the orbit combine to create an equilibrium. As Webb orbits L2, the telescope stays in line with Earth as it travels around the Sun. The telescope's optics and instruments need to be kept very cold to be able to clearly observe the very faint signals of very distant objects. This location is perfect for Webb's sunshield to block out light and heat from the Sun, Earth, and Moon. Unlike the Hubble Space Telescope, Webb's orbit keeps the spacecraft out of the Earth's shadow, making L2 a thermally stable location for the observatory to operate. Webb will operate within its field of regard. The field of regard refers to the angles the telescope can move while staying in the shadow of the Sun. Each of Webb's instruments has its own field of view. The field of view is the area of the sky an instrument can observe. Webb's fine steering mirror is moved so that an object can be observed by the different instruments. This prevents the whole telescope from having to repoint itself to do so. The commissioning process will be complete approximately 6 months after launch, at which time Webb will start its science mission, helping to uncover more of the mysteries of our universe.
So there you have it. Webb is in a stable orbit now at Lagrange Point 2. So Amber, Scarlin, that leads us to the big question for today. What can we expect next for Webb's mission?
Well, now we just continue to cool down. In order for our instruments and fine steering mirror to function at optimal capacity, we need to reach a set temperature range. And then we'll also be aligning our primary mirror before moving on to the instrument package.
And of course, after all of that comes the fun part. I mean, this is all fun, but for me, the science is the fun part. And so we expect the first science images from JWST to come back in about 5 months. So be getting excited, getting ready for those to come back later on this summer. And we can expect really spectacularly beautiful images to come back from this awesome new telescope. But beyond that, they're going to be amazing scientifically, of course. The first year of JWST science observations has already been planned, and we will be looking at things in the universe ranging from objects within our own solar system all the way out to searching for the very first galaxies to be born after the Big Bang and everything in time and space in between. It's going to be awesome.
Wow. I mean, the fun has just begun. And it's very cool to hear that we already have this first year of science ironed out. And I'd like to go back, Scarlin, you mentioned that over the next 5 months, Webb will continue to cool down its instruments. So Webb has been traveling through space for the past 30 days. Can you help, which is already very cold, so can you help us understand why it takes so long for Webb to continue cooling down to this correct temperature?
Yeah, that's actually a great question. I think sometimes it's easy for us to assume that because it's space and it can get really cold, in some places reaching absolute zero, why wouldn't we just instantly freeze up, right? Especially with this humongous sun shield. And the sun shield did indeed increase our cooling rates quite a bit. But we have to remember that the space environment is not like it is here on Earth. We have heat transfer processes here on Earth like convection and conduction, and in space we're limited to radiation. Therefore, the heat dissipation takes a lot longer.
Wow, thank you for that explanation. Because, like you said, I mean, you can test it as much as you want on Earth, but when you get to space, it's a whole different ballgame. And so, another thing that I want to go back to over this next 5 months is that you mentioned that we need to align Webb's mirrors. So these 18 hexagonal pieces all have to come together. Can you walk us through how that works?
Right, so these 18 hexagonal mirror segments need to be pointed in one direction so it can flow as one giant 6.5 meter mirror so it can get as much coverage as possible. So now that the mirrors have been cleared off their launch restraints and moved slightly away from the telescope structure, starting off, each segment sees independent light sources because they're essentially facing different directions. So we have to align them to work together. So right now they have different images in different locations. So for example, when you look at me, you see one of me. But if your eyes weren't working together, you may see two of me. So you can kind of think of it like that. Or say you had a hand mirror you were looking into and it had different segments and each segment was slightly off, you would see a distorted view of yourself. But if it was a nice sleek surface, then you would see an accurate view of yourself. So you can think of it that way. We're going to be using actuators and radius of curvature motors that are located behind each segment to make really small, tiny movements, moving them just microns and nanometers. So our smallest movement would be about like 10 nanometers, and I've heard that being described as 1 out of 10,000th thickness of human hair. So very tiny movements. That's how much control we have with these motors. They provide us 6 degrees of freedom. And we're going to move each mirror very carefully, and we're going to determine which images are reflecting from which mirrors. And then through the wavefront sensing and control process, we'll be able to achieve full alignment and fully align our iconic gold mirror and finally focus the telescope.
Wow, thank you. That was a really great explanation of that. And to hear that the movement is as thin as a human hair. I mean, the technology on this telescope does not cease to amaze. And so I'm actually going to take a step back because we are getting a ton of great questions coming in online. So let's just get right to them. Our first question is going to come from Kevin on Twitter, who asks, approximately how long will JWST take to accomplish one orbit around Lagrange point 2? Scarlin, could you expand on that for us?
Could you repeat the last question? The audio cut out for me a little bit.
Yeah, sure thing. So we have Kevin on Twitter who's wondering approximately how long will it take Webb to accomplish one full orbit around Lagrange point 2? Scarlin, do we still have you there? Okay, it looks like we lost Scarlin for a second. So while she is coming back in, Amber, do you happen to know the answer to this question?
So I don't know the exact answer off the top of my head. We'll need the engineer back to answer that. Remember, I'm an astronomer. But what I do know is that orbit around the L2 point, it's a huge orbit. And so it sort of orbits around this sort of imaginary L2 stationary point during the course of its orbit around the sun. So the telescope essentially orbits the sun in line with the Earth, and it takes, of course, a year to make that orbit around the Earth or around the sun along with the Earth. But then, along the way, it's making this long, big circular orbit around the L2 point.
Great. Thank you so much for that. And when Scarlin comes back, Kevin, we will be sure to see if we can get the answer to this question for you. So let's move on. We have Stan on Facebook, Amber, that's got a great astronomy question. He wants to know, could you tell us a little bit more about the decision-making process involved with selecting Webb's targets and who decides the priority and allocates time for each of these points of interest?
That is a great question. And the answer is that it is purely sort of democratic. Anyone in the world can propose their best idea on where to point this telescope. That's how it works with Hubble right now, and that's how it's going to work with JWST coming up in the very near future. So basically, once a year, astronomers from around the world sort of get together and think up their best ideas of where to point the telescope so that we can, learn new things about the universe. And they write proposals, submit the proposals, and then another team of astronomers reviews the proposals and sort of ranks them. And this is all done anonymously, so there's striving to be fairness in the process, so that at the end of the day, the best ideas get prioritized, and that's who gets time on the telescope. Now, the really great thing about this data that's going to come back from JWST, same thing with Hubble, is that a lot of times the astronomers who win time get a certain amount of proprietary time, so they get access to the data for 6 months, maybe a year. But after a year, it all becomes public. So anyone in the world can use that data to do science, which is awesome. And then a lot of the data that's taken during the first year of JWST's lifetime, particularly during the first few months, is going to be available immediately to everyone.
Wow. I mean, there was so much awesomeness in that. It's so cool to hear that Webb's data, this was already such an international mission, and that this incredible piece of technology gets to be used and the love is shared by everyone around the world. And to actually follow up to that, talking about what objects that James Webb will be looking at and some of its targets, Steve on Twitter is wondering, will JWST look at objects in our own solar system as well?
Absolutely. So JWST has the ability to look at objects from Mars on out. So it can, of course, again, it's orbiting just outside the orbit of the moon. It's about 4 times further away than the moon. So it always has to be pointed out towards deep space. It can't ever look back towards the Earth. So, for example, it could never observe Mercury and Venus, but it can observe Mars and everything on out. And in fact, during that first year of observations, we have detailed plans to look at lots of objects in our solar system, from Mars, some of the moons of the outer planets. So there's a whole list that you can find online of objects within our solar system that JWST is planning to study during that first year.
Nice. And you say that we can look online. Is there a specific website that people should look forward to find this information?
Absolutely. So the Space Telescope Science Institute is where our Mission Operations Center is located. And if you go on their website, stsci.edu, that's where they have listed all of the different observing programs that are planned for the first year. So you may have to go a link or two deep, but you should be able to find it pretty easily. Or you can just Google JWST Cycle 1. So we call the cycles year by year. So Cycle 1 observations are what that first year is going to be.
Thank you so much for sharing that. I know a ton of viewers are going to be excited to hear that, because that is a question we get so often on social media. So, Amber, we have another question from Facebook. Danielle asks, is the exposure time in infrared different than it is in visible light for data acquisition?
Absolutely. So the wavelength of light that you're looking at always does come into play when you're planning these observations. And that's for several different reasons. But one of the fundamental reasons is just because objects in the universe emit these different wavelengths of light at sort of different strengths. Okay, so you can think of one object might not be very bright in the visible light, but might be in emitting a lot of infrared light. And in fact, some of the things we want to look at with JWST are going to be great to observe with this telescope for that specific reason, that you can't really see them in visible light or other wavelengths, but you can see them in infrared light. And so yes, because objects emit at different sort of power at different parts of the wavelength range means that we'll have to sort of calculate those different exposure times. And you can see right now, actually, one of the things I love about these infrared images, people always ask if they're going to be pretty, which is a valid question. And this, what you see on the screen now, is a near infrared image from Hubble. So Hubble has a little bit of capability in the near infrared, and this is a near infrared image of the Eagle Nebula, or often called the Pillars of Creation from Hubble. And what infrared light allows us to do is essentially peer down into those dust clouds that you can't see through with visible light, and allows us to see the stars being born. So when people ask if these pictures are going to be pretty, I always point them to this image, because isn't this is like a beautiful, spectacular image.
I completely agree. And oh, hey, Scarlin, so glad to see you back and online.
Technical difficulties.
No worries at all. Amber, I'm going to toss you one more question, kind of in the same light. We have Mark on Facebook who wants to know that due to Webb's position at L2, is there anything we won't be able to see?
Yeah, so I kind of touched on this a little bit, but because it is at that part of space, and because it's an infrared telescope, of course, the mirrors always have to be pointing outward, away from the sun. We can't ever point the telescope back towards the sun, because that would essentially fry our detectors. And so that means we can't look back at the moon, the Earth, Venus, Mercury, or the sun itself, of course. But everything else from the orbit of Mars on out is fair game for this telescope.
Wow. I mean, that gives us a lot to look at. Thank you so much. And so, Scarlin, Amber was just telling us a little bit about what we can expect for Webb 2 image and how that process really works between the infrared and the visible light. But we have a question from Mike T on YouTube, who asks, how long does it take for communications to transfer to and from the telescope? Do you have any insight on that?
Well, that's a very specific question. I would probably have to defer that one to the comm team, but we use these massive, powerful antennas from the ground to relay the signal from the computers in the Mission Operations Center to the telescope. So from the control center, we are sending commands to the telescope. Any activity that it performs, we're commanding from the control center. And then once the telescope performs what it needs to do, we are monitoring real-time telemetry down on the ground.
Wow, thank you. And so back to just monitoring this telescope systems, and a little bit earlier you mentioned that in the immediate future, the next 5 months, Webb will need to cool down to a specific temperature in order for its instruments to work. And so we have Anthony on Instagram who wants to know specifically how much time till Webb actually cools down to this correct temperature.
Right. So it's about 40 Kelvin. I believe it takes about 98 days for the instrument's mirror to cool down to temperature.
Wow,
good question.
That is very cold. That is very cold. Thank you. And so and a follow-up, Twit app on Twitter asks, has the gradual cooling down of Webb over the last week been according to the simulations? Has it happened as y'all thought it would?
Yeah, of course, it's never perfect because it is a simulation. But yes, it has been almost just as expected. We have had our cooling rate increase quite a lot from the deployment of the sun shield, and everything is going marvelous, really.
Nice. I mean, that is what we love to hear and hope it continues that way over these next 5.5 months, fingers crossed. And so another question we have is from Justin on Twitter, who asks, are there other observatories in L2 besides JWST? Scarlin, you want to take this one?
Amber, do you want to take this one actually?
Sure. Yeah. So there are other observatories out in this part of space. There's the European Gaia Observatory is out in this part of space, and in fact, we've been able to learn about, for example, the micrometeorite situation in that part of space, thanks to some of these other satellites. So that's a question I get a lot: is are we worried about micrometeorite impacts in that part of space? And the short answer to that is no, not really, because it's a semi-stable point. Stuff doesn't tend to collect there. But part of the reason that we know that for sure is because we've been able to sort of assess it from other spacecraft that are in that part of space. So yes, we do have other satellites out in that part of space.
Nice. Thank you. Thank you so much for that. And thank you too to everyone submitting your questions today. If you are just tuning in, we really encourage you to participate live in today's show by dropping a question in the chat stream wherever you're watching from, or by using the hashtag #UnfoldTheUniverse on social media. Scarlin, Amber, don't go anywhere. We will get back to you in just a second. But first, we have another way for those watching to participate in the Webb mission. We know that 5 months is a long time to wait and wonder about what Webb will discover. Show us what you believe the Webb telescope will reveal by creating art. You can sing, you can paint, you can dance. The universe is literally the limit in this case. So share a picture or a video of you and your creation online using the hashtag #UnfoldTheUniverse. You'll have a chance to be featured on NASA's social media page and also the NASA website. Take a look at how it works.
Hi everyone, I'm Kelly Girardi, and this is Delta V, and we're kicking off the Unfold the Universe Challenge with NASA and the James Webb Space Telescope.
The Webb telescope is NASA's biggest and most powerful space telescope ever. It's going to help reveal our universe like never before.
Delta, what do you think we'll discover?
I think we'll see stars, planets, and galaxies. I can't wait!
NASA is hosting an Unfold the Universe art challenge. Use your imagination to share what you believe the Webb telescope will find. It could be a drawing, a poem, a song. You could be creative.
I drew a picture of what I think the telescope will see. This is the telescope, and these are our planets and stars.
Wow, Delta, it's beautiful. I can't wait to see what everyone else comes up with. You can share a photo or a video of your art and what you think Webb will discover using the hashtag #UnfoldsTheUniverse.
Go, Webb, go!
I love this art challenge so much. I have had the amazing honor of being one of the people that gets to sift through some of these submissions, and each creation has been so incredibly unique and really just showcased people's individuality. It's been inspiring to see everyone's wonder and creativity from around the world, people of all ages and from so many different countries. For everyone that has already contributed, thank you. Who knows, maybe your creation really will be what Webb reveals. So keep them coming online. You can submit them using the hashtag #UnfoldTheUniverse. We love to see them, so we encourage you to join. Okay, let's bring back Amber and Scarlin because we still have so many great questions coming in online. So the next question we have is a person on Twitter who asks, will JWST look at the Hubble Deep Fields? Amber, this is a perfect one for you. Will they be able to see it?
Yes, absolutely. In fact, one of the primary drivers for building JWST back, years ago, a couple of decades ago, was to be able to find the very first galaxies that were born after the Big Bang. And by looking at images like the Hubble Deep Field, Ultra Deep Field, we've been able to push back and see very distant galaxies. But at some point, we sort of come to the edge of what Hubble can see. And JWST was specifically designed to help us find those first galaxies beyond what Hubble is capable of seeing. And the Hubble Ultra Deep Field and some of the other deep fields that Hubble has observed are these places in space that are incredibly rich in data. So not only do we have data from Hubble, we have data from other observatories. We have X-ray data from Chandra. We have infrared data also from Spitzer. And so all different kinds, all different wavelengths of data in these fields. And so the fields themselves are incredibly rich, and adding JWST's deep infrared data on top is going to help us both hopefully find those very first galaxies to be born over 13.5 billion years ago, as well as just add to the depth of knowledge that we can learn about galaxies and about galaxy evolution in these very rich fields.
Wow. I mean, you mentioned 13.5 billion years. It is just incredible what this telescope can see. And so we've talked about Hubble Deep Fields. We've talked about some of these first observations. And that leads me to a really great question from W.F. Swigert on YouTube. Scarlin, this is a great one for you. Are the mirror alignments and adjustments intended to be permanent, or will they need to be some adjustments depending on what Webb decides to look at?
Yeah, so where it's designed to be adjusted anytime that it needs to be. So we will have to align them throughout the life of the mission. So it's not just right now. It's a continuous process just to make sure that they're always perfectly aligned.
Wow, it's really like we really do have our own little transformer in space. That's so cool. And so, I have a great question for both of you. Emma Fitzpatrick on YouTube states, "Hi, my 10-year-old son, Dara, is an inspiring engineer and is really inspired to watch you tonight. What advice would you give for him to someday work on projects like this?" Scarlin, as our engineer, do you want to kick it off?
Sure. I would say work very hard. Don't give up. Engineering can be hard for a reason, but then we get amazing gifts like JWST. So it's always worth it. Just continue on your path. Make sure you have a great support system. And like I said, never give up. Reach for the stars.
I love it. And then Amber, we also have a lot of aspiring scientists. Do you have any advice for anyone out there who might want to follow your footsteps one day?
Yeah, well, Scarlin just gave some really great advice, and I think that holds for science as well. And one specific thing she mentioned that's been really important for me is that support network. So I know that mentors have been incredibly important to me to help me, get to where I am in my career. And so I think it's super important to find people all along the way, no matter what stage you are in your education and your learning, to find people that are willing to help you and support you and sort of help you make it to the next step, because none of us do any of this by ourselves. It's a group effort for sure. So find good mentors. That is probably my top piece of advice. And then if I could jump back to a previous question, because I now have an answer. So one of our engineers texted me, thank you, Mike Menzel, and said that the time it takes to orbit L2 is 180 days, which I didn't know until just now. So it actually takes half a year almost to make that full complete orbit around L2. So I knew it was a long time. I didn't quite realize it was that long. So super interesting.
Yeah, wow. Thank you for that. And thank you, Mike. And so moving on, we have a great question from Penny on Facebook. Amber, if you want to take this one, feel free. She wants to know, how will the public access the images once they're acquired?
Yeah, so that's a great question. That also will be housed at the Space Telescope Science Institute, which is where Scarlin works. So they are our sort of repository for housing the data for the telescope, also for Hubble. So that will be the place to go to get all of the images. And of course, as we make discoveries, as astronomers make discoveries along the way with the data, we will, of course, provide those fully produced beautiful images to the public as well on all of NASA's channels.
Great news. Thank you, Amber. So our next question comes from Connor McEwen on Facebook, who asks, will the JWST correct for photons from the sun pushing on the sun shield? Scarlin, do you have any insight on that?
We will get a lot of solar pressure, solar radiation pressure on the sun shield. But as far as the photons and all of that, I think Amber would probably be a better source.
Yeah, so as Scarlin mentioned, that solar radiation will push on us. So that's, the sun shield is essentially a solar sail. And so, we will make small corrections during the course of operations to make sure we sort of offload that momentum that builds up due to solar radiation on the sun shield. Yep, that's going to be a regular part of our operations.
Yeah, I think I misunderstood that question. Completely agree with Amber on that one.
Great, thank you so much. And on the topic of new technologies really built for this telescope, we have a question from Brent on Twitter who asks, what are some other new technologies that building the JWST telescope has created, especially transformative tech that might have changed our daily lives? So basically, he's looking for spin-offs. Has any other new technology been created through the building and operation of Webb? Scarlin or Amber, whoever wants to go first.
That's a great question. I'm curious about.
Yeah, so the one that comes to mind that I know of that I know NASA has talked about is the fact that because these mirrors have to be aligned so precisely, the shape of the mirror has to be absolutely perfect. And so that'll happen after this upcoming 3-month mirror alignment process. So if you can imagine if the whole 22-foot mirror was the size of the continental US, the biggest bump on this mirror is going to be about 1 inch or 2. Okay, so it's very, very smooth, the surface of the mirror. Now, it turns out that confirming that smoothness and even measuring the smoothness is really, really hard to do. And so just the technology that we had to develop to measure the smoothness of the mirror has actually already been used in the medical field, in the field of ophthalmology. So eye doctors have used this technology to help measure the shape of the human eye. And this has already gotten benefits in making eye surgery much shorter, much more efficient, and much safer. So that's one example of a sort of spin-off technology that's come from the development of this telescope that really plays real effects in the real world.
Wow, that is really cool. Thank you, Amber. And to kind of stick on this topic of mirrors, Scarlin, we have a question from Brian on YouTube who asks, who's looking for more clarity about where Webb's 18 mirror segments are supposed to be pointed. Specifically, he's wondering, are all 18 segments pointed in 18 different directions or pointed in one direction and aimed at and targeted at different focal points?
Yes, that's a great question. So they all the 18 segments have to be aligned to make that parabolic, that iconic picture that you've all seen. It's a bit of a concave mirror there. And basically they all have to be pointed in the same direction. The light is going to be reflected onto the big giant mirror, and then it will be that will beam into the secondary mirror of the telescope, which will then go back into kind of like that nose in the middle of that giant mirror, which holds the tertiary mirror and fine steering mirror. And so, yes, it's that parabolic shape that you see there. And that's what we need to maintain the entire time. The pointing is done with our attitude control system.
Okay, great. So yes, the mirrors are all actually pointing in the same direction. Thank you. And so moving on, we have a question from Manuel on Twitter who asks, can Webb's observation schedule be adjusted in case a discovery shifts the scientific priorities? Amber, do you have any insight on that?
Yeah, absolutely. And in fact, that sort of flexibility in scheduling is built in. And so in astronomer speak, those are called targets of opportunity, or TOOs. And so if something super exciting, something sort of short-lived happens in the universe, and we want to pause our observations and point the telescope in that direction, we have that flexibility built into the schedule to be able to do that. So a good example would be like if a supernova goes off, or some other event like that happens sort of quickly. So yes, we have that capability built in. There are some constraints on that. So you can imagine as the telescope orbits around the sun, again, we sort of talked about it can't ever look back towards the sun. So it can only see a part of the sky at once. And so if it just so happens that your object of opportunity is in the wrong part of the sky, we wouldn't be able to do that. But for the most part, in general, we do have the flexibility to sort of pause the scheduled sort of routine operations to observe things that happen in the universe that sort of happen all of a sudden.
So sticking on kind of these shifting in case of a discovery, Robert on Facebook asks, as part of Webb's mission, scientists will be analyzing the atmospheres of exoplanets on possibly habitable conditions. I know that is something a lot of people are very excited about with this specific mission. And so he wants to know, how will Webb collect this data of these atmospheres, and what kind of things will scientists be looking for specifically?
So the way that we study exoplanet atmospheres is by watching the planet transit in front of its star. And so this is how we've been able to discover so many of these exoplanets in our galaxy, is by watching a star and watching for the light to dim in a periodic way. And so that's how we know that a planet is orbiting it. And so you see the simulation on the screen now. You can sort of see that teeny tiny little planet crossing in front of the star. And you can even get a sense of just how hard this is. So essentially what we're going to be doing is watching that planet pass in front of the star, and then watching the starlight filter through that planet's teeny tiny little thin atmosphere. It's really, really difficult, very difficult observations. But with JWST, we now have new capability to do this better than has ever been done before. I study how stars and black holes form in distant galaxies and how galaxies change over time. So exoplanets are pretty far from my own personal research, but I think that some of the exoplanet science that JWST does is going to be some of the most outstanding, surprising, incredible things that JWST is going to do. And it turns out that an infrared telescope is perfect for these observations, because some of the things in these atmospheres that we really care a lot about happen to fall in the infrared part of the spectrum. So chemical signatures like carbon dioxide and methane and water vapor, all of those that could be sort of, pointing towards the building blocks of life.
Wow. I mean, that is incredible, Amber. Thank you so much for just painting that picture for us about how this is going to happen. And I think it's so cool to just go back to the fact that Webb is making all of these observations at a stable orbit at this Lagrange point 2 in space. And so, Scarlin, this whole show, we've been talking about Lagrange point 2. I have a question about that. How can you even orbit an empty point in space?
So it's actually the reason we chose that location. It's because, it was already explained in the video what Lagrange point 2 is, but because of the gravitational pulls, the telescope is able to float much easier in that bit, and we don't have to use much fuel to maintain ourselves there. So that's basically the gist of it. And you're seeing that in the simulation there. And you see the telescope orbiting L2, orbiting around the sun there in this sort of halo orbit, not exactly a circular orbit, more halo.
Thank you for that. And so we have our next question from Morali on Facebook, who wants to know, will James Webb provide information about the Big Bang? Amber, I think this is a great one for you.
Sure. So when we're thinking about, looking back in time, what the real thing we want to find out with JWST is to see the first galaxies that were born after the Big Bang. And so we won't be looking back, so to speak, to the very quote unquote moment of the Big Bang. But what we're really interested in seeing is how what happened in the Big Bang gave rise to those first galaxies. And that's a part of space that we've never seen before. So, of course, we've seen images of the sort of the glow, the remnant of the Big Bang in the cosmic microwave background. But at that point in time, there was no stuff, right? There was just radiation. There was just elements. And so what we're looking for is the point at which that early hydrogen and helium, what was the components of the Big Bang, when that hydrogen and helium first started forming the very first stars and galaxies, the first stuff in the universe, the first objects. And so that's what we're going to specifically be looking for with JWST, is this first epoch of galaxies that formed after the Big Bang.
Wow. And so, Amber, to get this right, we have never done that before, have we? We have never looked that far back.
Right. Yeah. So with Hubble, we've talked a little bit about the Hubble deep fields. And with the deepest images we've been able to take with Hubble, we've been able to see back pretty far and see some very distant galaxies and see those galaxies as they were in the very distant past. So we have been able to see very distant galaxies with Hubble, but we've sort of come up to the edge of what Hubble can do. We can't see any further because these first galaxies are emitting their light. The light now is only in the infrared part of the spectrum. So even if we had a huge, visible light telescope in space, an even bigger one, we still wouldn't be able to see these galaxies because their light is now totally in the infrared part of the spectrum. And so yeah, we'll be able to see that first epoch of galaxies that's more distant than what we've been able to see with Hubble.
That is so exciting. Thank you. Thank you so much for that. And so we have a fun question for both of you. Scooby Arthur on YouTube asks, what are you hoping for the very first discovery? Scarlin, I'll kick it to you, and then Amber, would love to hear from you next.
I think for me, what's most fascinating is to think that now that we're going to be able to through all of the gas and fog in space that we weren't able to before, mid-infrared, that discover things that we didn't know existed. So that's super fascinating to me. The exoplanets, learning about other planets that are made of rock, like us, like Earth, that could have oxygen or signs of carbon dioxide, and us that could help support life. That's just interesting. And know about our origin, how we got here.
Yeah, and for me, sort of in a similar vein, I mean, we have all of these very specific questions we want to answer about the universe, right? And we have this first year of observations planned where we hope to start to answer some of those questions. Things like, how did planets and stars form, and what's going on with some of the objects in our solar system? And again, all the way back to finding those first galaxies. So we have these very specific questions that we want to answer. But for me as a scientist, the thing I am most excited about is the discoveries that I know we will make that are completely unexpected. It's like there are these surprises out there lurking in the universe, things that we've never dreamed of. And I think we'll find those. And I think that prospect of finding things that completely surprise us, that sort of change the way we understand the universe, that is what I'm most excited about with this telescope.
Wow. Thank you both. I mean, I completely agree. And also, I know, Amber, you've done a little bit of work with black holes. And so just seeing what this telescope even reveals about those is going to be incredible. So much great science to come for Webb right now. So for Scarlin, I've got a question for you from AvGeek on Twitter. who asks, how excited does an aerospace engineer get about the astronomical aspects of a mission like this? And I can repeat that as well if you need it.
Super excited, even though you can't see it right now. I remember during the deployment phase, I was on the edge of my seat. It was like watching, the Super Bowl for me. And pop champagne while I was in the control center, but obviously that's not a good idea. But definitely when I got home, it was a big celebration. I'm really over the moon about how amazing everything has been going up to this point, and I'm so excited for the future.
Nice. And Amber, how excited does an astronomer get for the aspects of a mission like Webb?
Yeah, well, I mean, we're obviously excited about the science. Of course, all of us astronomers are. But for me, one of the coolest things about working at NASA is that we do work alongside these brilliant engineers that have built this awesome machine that is going to, I think, change the way that we understand the universe. And just to be a part of that, to be, to be able to walk across campus and see the telescope being built a few years ago really gave me a much better understanding. Again, as a scientist, it gave me a better understanding of just what goes into engineering, to building these types of things. It's absolutely incredible. I think this is a moment in our history as humans that we can just, as a society, as a species, be so proud of, because we've built this amazing, beautiful machine that is going to transform our understanding of the universe. And I think it's incredible.
So well put. Thank you both for that answer. And so, Scarlin, I have another follow-up for you. Glitched Robot on Twitter asks, what can you tell us about JWST's secondary mirror? Is it the same material as the primary mirror?
So it is another gold mirror, and it's a convex flaring mirror, about 2.42 diameter, I believe. Good question.
Yeah, thank you for that, Glitched Robot. So moving on, Amber, we've got a question from an 8th grade student who wants to know if JWST will be used to find or identify large objects in the Kuiper belt or the Oort cloud.
Absolutely. So that part of the outer solar system is something we're definitely planning to use JWST to study objects and to look for objects there. So like I said, the whole solar system, basically from Mars on out, is fair game. And so we absolutely will be looking for objects in the outer solar system with this telescope.
Wow. I mean, thrilled for what's to come. And unfortunately, that is all the time that we have for today. But Amber, Scarlin, thank you both so much for your time today. It was so great to hear your insight on this mission, and we really appreciate it.
Thank you. It was really an honor to share with you all.
Yeah, thanks so much. This has been fun. So exciting.
And a big thank you to all of you who joined and asked your question today. Make sure to stick with us as Webb gears up to unfold the universe and start sending back science and data. Visit go.nasa.gov/Where is Webb to keep up with the telescope's milestones, the observatory's temperature, and its location in space. The team will also be posting regular updates to the @NASA social media accounts. That includes Twitter, Facebook, and Instagram. We will be back to answer your questions live on this show once Webb releases its first images. So stay tuned and go Webb.